In this lecture, we're going to discuss the different families of elements on the periodic table. We're going to explain why all elements in a family have similar properties, how to recognize the properties of each family, and how to use the periodic table to identify an element's family, such as the alkali metals, alkaline earth, transition metals, metalloids, otherwise known as semiconductors, halogens, and noble gases. To start with, we should know that an element family means a group of elements with the same number of valence electrons and very similar properties. So why do all elements within a family have the same properties or similar properties? Well, the answer has to do with the number of valence electrons. So if you can find the electron configuration for any element or group of elements in a family or group, you'll see that they have the same number of of s and p electrons in their outermost energy level, and this is going to be their number of valence electrons. This determines their chemical and physical properties. And again, the 6 families that we're going to learn about are these ones listed here. The first ones we're going to look at are the alkali metals, which is the very first column on the left, as you can see here on the periodic table. The alkali metals include hydrogen, lithium, potassium, sodium, cesium, rubidium, and francium. So all the elements in the first column. They all have one valence electron. Their physical properties, as you can see in the pictures here, are that they are soft, dull, and solid. If you were to look at the atom's atomic radius, they have the largest radii of all the elements in their period. In terms of chemical properties, they are very reactive. However, they have the lowest ionization energy. They are very famously reactive with water. They're reacting with the oxygen in the water, and so they are stored, as can be seen in this picture of the left in sodium. They're stored in oil just to make sure that they don't react with any water or oxygen in the air. And we can see from this picture that they are very soft. Now when they become ions and they are combined with other ions such as sodium chloride, their properties are going to change. So these properties we're looking at are only for the pure elements. We can also see that hydrogen is on that list. However, hydrogen has properties of both the alkali metal and the halogen families. So hydrogen could also have been placed over here in terms of its properties. And when we discuss the halogens, you'll see why hydrogen would also fit well in that category. So because hydrogen has one valence electron, it is technically placed in with the alkali metals. However, it does have some similar properties as halogens, as we'll see later. The second group we're going to talk about are the alkaline earth metals in column number 2. This includes beryllium, magnesium, calcium, etc. All of these atoms have 2 valence electrons. Their properties are very similar to the alkali metals. They are also soft, dull, and solid. They have large radii, but not as large as their neighbors to the left. They are less reactive and also have a low ionization energy. So they are very similar. And you can see in this picture of magnesium, calcium, and barium that they're all very similar looking, not very shiny, kind of dull, just kind of look like rocks. They're not shiny crystals like some of the transition metals will be when you see them. And this all has to do with them having only 2 valence electrons. The third category is a very broad one, the transition metals, and this includes the transition metals in the F block, the lanthanide and actinide series. The properties we're going to discuss really only are relevant to the naturally occurring transition metals. The synthetic ones that are made in a lab, most of them do not have properties that are known, either because they have not they are new and their properties have not been discovered or have not been analyzed, or for the most part it's because not a large enough sample has been made in order to accurately determine what the properties are. So the transition metals would include everything from scandium and titanium on the left to zinc on the right, including cerium and thorium and other of the elements towards the bottom of the D and the F block. These also in general have 2 valence electrons. Some of them have 1. Some of them will also have exceptions. But in general, their physical properties are that they are harder than the alkali and alkali earth metals. They tend to be more shiny. They are also solid at room temperature, with the one exception of mercury. They are also magnetic, and they are very good conductors of heat and electricity, as opposed to the other 2 metal categories which are not. Chemically speaking, they are less reactive than the alkali and alkaline earth metals, and they also have low ionization energies. And you can see just from this grouping of pictures that there's very different colors that are involved, but all of these are much shinier and more lustrous than the other metals, the alkaline and alkaline earth metals are. Some of them are gold, such as literally gold is gold, or a golden color such as copper. This uranium has a bit of a reddish tinge to it. And some of them are a little bit silverish, but they all tend to be very shiny and lustrous. Some of them are very malleable and can be flattened, such as gold is very soft, and some of them are harder. So as I had said, the properties that we were just looking at are really only for the naturally occurring elements. So for example, if you were to look at many periodic tables that talk about the different properties, for the synthetic elements, they're not going to have a picture. For example, this one that I found online, some of its properties are unknown, such as its density and its boiling point, and many of its other properties, because there is not enough of it. So what was quoted on that page is that this photograph of Alfred Nobel appears representing nobelium, which is named after him. This highly unstable element can't reasonably be photographed, which is why there is no picture for that, and why many of those synthetic elements have unknown properties. The fourth category we want to discuss is the metalloids or semimetals, and this makes up the border between the metals and the nonmetals. In general, as you can see by the titles, everything to the left of the metalloids is a metal. Everything to the right is a nonmetal. So the metalloids make up that category of the gray area in between the two. Boron, silicon, germanium, astatine, etc. These are the metalloids or semiconductors. They have 3, 4, or 5 valence electrons, and their physical properties really reflect where they are in between the metals and the nonmetals, because they have properties both of metals and of nonmetals. For example, they are shiny and conductive, much like the metals are. However, they are brittle. They are not soft and malleable like a metal would be. They have medium radii, so they're not very large, but they're not as small as the nonmetals. And they are good conductors, but only at certain temperatures. Their chemical properties are likewise similar to being in between the metals and the nonmetals. They have a medium ionization energy, not high like the nonmetals and not low like the other metals. And they may either give or take away electrons. So some examples would be germanium and arsenic. We can see that they are very shiny, they look very sharp, and they are, you could see that they are very brittle. If you were to take a piece of this germanium, for example, and try and bend it, it would snap. And this is a picture of a silicon wafer, which is etched into it are hundreds, it looks like from this picture, of little chips that could be used in computers or in cell phones. And so a lot of when you hear the word semiconductor, most people usually think of that as being related to electronics, and that is the case. These are the elements often used for many of our modern electricity, but that could be changing in the future. The next group I want to talk about is the halogens. They are over here next to the noble gases. So the halogens kind of include hydrogen. We talked about that earlier. Fluorine, chlorine, bromine, iodine, and astatine. They all have 7 valence electrons with the exception of hydrogen. The physical properties are that they are nonmetals and they are not solid. So they are liquids or gases at room temperature. In each period, they are the smallest of the radii and they are not conductors. Chemically speaking, they are also very reactive and they have high ionization energies. Here's 3 examples. Chlorine and bromine. This shows the gas of the chlorine and the bromine gases in a glass tube. And this shows iodine. Iodine is it's not really solid, it's not really liquid, it's kind of slushy, and it very rapidly will vaporize into a gas. And so that's what we see here is this kind of a pinkish gas that is coming off of this iodine slurry. Hydrogen acts similar to a halogen in terms of its chemical properties. Most of these, when we learn about ionization, when we learn about ionizing, most of these are going to gain 1 electron to become an ion that has a -1 charge. Hydrogen can do that. Sometimes it will do that and it will become a hydride ion. Oftentimes it will lose one electron and become a hydrogen ion, which will have a +1 charge, which is what the alkali metals will do. So this is the reason why hydrogen can act as both a halogen and an alkali. Our final category is the noble gases on the right side of the table. That includes helium, neon, argon, krypton, xenon, and radon. They all have 8 valence electrons, with, of course, the exception of helium, which only has 2. Their physical properties are that they are all gases, they are all nonmetals, and chemically speaking, they are not reactive. They have the highest ionization energy because they refuse to let another atom remove one of their valence electrons, but they themselves will not react with another element, which is why they are considered to be inert or noble, because they will not react with or interact with any other elements. And so to take a picture of them, they would all be gases. So they're very famous for being used in neon lights. So for example, neon lights are named after neon, and this is what all of their gas diffusion tubes would look like. So there are 2 other categories that don't really have a specific name, but we should mention. There are the other metals and other nonmetals that fill in these categories, where carbon, oxygen, fluorine, lead, aluminum, tin. So they don't have specific names. They're just sort of in the other category. And their valence electrons vary by column, and their physical properties are pretty generically similar to the other metals and nonmetals. So for example, the aluminum, gallium, thallium, they, as you can see, they are similar to the other metals in that they're shiny, they're lustrous, they're not particularly good conductors of electricity, these 3 examples, but you can see by looking at them that they are definitely metallic. These 3 nonmetals, phosphorus, sulfur, and nitrogen, follow in general the nonmetals. Nitrogen is a gas in its elemental form, but phosphorus and sulfur are both solids. They are not conductors of electricity. They do not conduct heat. They melt at very low temperatures. So they are consistent with the other nonmetals. They just don't fit into either the halogen or the noble gas categories. So to look at a trend of metallic character, if we were to look at all of the elements, and this is a great periodic table you can find at this website down here, and this website also has information on each one of the elements and lots of great detail that I recommend you look up. We can see that they go from being very soft, very not crystal-y metals on the alkali and alkaline earth, to becoming more crystal-like, more shiny over here in the transition metal area. We can see this stripe of very brittle, shiny, crystal-like, metallic looking metalloids. And then we have over here the nonmetals, which gradually become only gases and liquids. So the trend in metallic character is going to decrease from metals on the left and nonmetals on the right. And again, the reason they have the characters has to do with whether they are going to gain or lose electrons in order to have a full outer shell.